Hello, everyone. As previously mentioned earlier today, these challenges that we are facing are global population growth, it's growing exponentially, and the rapid urbanization. Alongside with that, there's lots of food that are being consumed that are need to be produced, but also there's lots of food that goes to waste and the organic waste itself. And it's important to understand what happens to the organic waste once it gets disposed, to have a better understanding and to avoid climate change, so to reduce climate change, sorry. uh so that's why I'm gonna talk about my project, the non-dispersive infrared sensor applications to track carbon footprint impact of municipal organic waste management strategies. I'm Alejandro Quezada, and this is a project supervised by Dr. Gordon Price, Dr. Dave Burton, Dr. Grant Clark, and Dr. Alan Thompson. As I mentioned before, there's lots of food or waste that are being just thrown into landfills, that are being incinerated, and this is a significant contributor to the greenhouse gases and the climate change. So this is important because due to its biodegradable components, the organic waste can be diverted and converted into composting or anaerobic digestion to add more opportunity to this waste to be processed and give us something useful like soil amendments or sources of energy like biogas or electricity. But it is more important to understand these decarbonization pathways deeply, because they could be different from country to country or from province to province here in Canada. There's different sources of energy nowadays, like electricity, like fossil fuel combustion or wind turbines. So to understand on a given system, which kind of energy is available in your region, and the potential to sequester carbon will be different as well according to the properties of the soil you are putting these amendments. So it's important to understand and to have a sense of what's happening in order to have accurate decisions in the future, to plan ahead, and just to be to have a better understanding of the process. This is why my project is focused on developing a framework to quantify the carbon footprint of two different organic waste management facilities here in the province of Nova Scotia, Canada, to evaluate the physical and chemical characteristics of the source separated organics that are the ones that come from the local commercial and industrial places that are being diverted and processed here in these two facilities that I'm assessing: a composting facility in Colchester County and an aerobic digestion that is present in Courthouse Hill Farm. To tackle this project, I divided these two facilities into different stages to have a better understanding of what's happening over the course of a year. For the composting, I have divided into 6 stages, and the anaerobic digestion, I have divided into 3 stages to be able to collect initial material, in process material, and final process material to have a better understanding. My focus, according to the circular economy, is once the project is disposed and it's generated, once this waste is generated, it's the process it takes once it gets into these processing facilities until we get a final product. But further research needs to be done, and it's undergoing, about when these soil amendments are then applied into the land, and then what's happening once they reach the final sites of the soil. This framework, the first step, it's a sample collection. For that, to aim for the direct sources of emissions, I have established a sample regime of 17 time intervals over 3 weeks, every 3 weeks, from May 2023 to June 2024. And I've divided subsamples for 5 composite samples for the composts, and 5 composite samples for the anaerobic digestion. And in addition, to track the indirect sources of emissions. Also, we're also surveying these facilities to ask for information about energy consumption, fuel usage, travel mileage, and number of vehicles. All of this information will be translated into CO2 equivalents. That is the current unit that is approved by the IPCC. This material that's coming will be divided for physical, chemical, and biochemical analysis. That will be the second step of our process. And normally 20% will be separate to be thawed, dried, and to homogenize the particle size to 1 to 3 millimeters. We also measure, according to the United States Composting Council methods, we're measuring total solids, bulk density, elemental analysis through LICO for total carbon, total nitrogen, carbon and nitrogen ratio, and also the organic matter analysis to complement the important part. Also will be the determination of potential greenhouse gas emissions at different decomposition stages. For that, we have selected two approaches. The first approach is a gas headspace analysis using a gas chromatography to monitor the potential CO2, CH4, and nitrous oxide production rates in milligrams of gas per hour. For that, we have chosen an incubation of 24 hours and 1 liter jars per sample. This is a in-lab approach, but it significantly has application to be able to do it on site. But this first approach is on the lab, and each jar will have two headspace samples. I will, like with a syringe, will take the samples through with vials after the 24-hour period. In the jars, we add 50 grams dry or 50 millimeters. The other approach, it's the respirometric system. That is the one that's currently it's more efficient because you have more than one data point, because in this case, after 60 minutes, we're able to log every 1 minute number of monitor the CO2 production rate. These sensors allow us to measure the CO2 milligrams per liter, the temperature, and the humidity at the same time. And it's the same process as the other one of the gas headspace. With this information, we're doing analysis of variance to determine the significance of source separate organics, state, raw, in process, and processed final, and seasonality over the 17-time intervals for the production rate for these methane, carbon dioxide, and nitrous oxide gases, for the total carbon, total nitrogen, or carbon nitrogen ratio. We want to track the differences of the production rates, because here in Canada, the winters are longer, so that could mean that the production rates during these seasons are slower than the ones in summer when the weather is humid and hot and warm, but it's only for short time periods, like 1 to 2 months approximately. This is how the results look like. The respirometric system shows multiple data points, as I mentioned, and 60 and the slope of these lines are the production rates, and we are able to transfer this information, comparing all these different stages into the 6 stages that we divided. And in this next graph, we're able to see how the production rates changes over one time interval for the composting process. And we can see how, as the material gets more processed, it gets more stable as well, and it has a peak. That means it's during its active processing of compost will be the compost production rate will be higher, the gases will be higher, the emissions will be higher as well. This information is important because with this data and these models, we can use these models to estimate and simulate scenarios that will provide support to policymakers in the future. And also this lab approach could be also applicable into the sites. That will be applicable not only to waste facilities, but also to the soil once it gets applied into receiving sites as soil amendments, and this will close the loop of the circular economy and allow us to have a better understanding of what's happening. And this standard protocol specifically about the waste processing could be also applied into different provinces or around Canada or different sites along the world of compost and anaerobic digestion. And thank you very much.